Hi everybody, it's me Dr. V, and it's a good day to talk about AP chemistry. In this webcast, we're going to talk about acid-base titration calculations. So this is really focusing on the stoichiometry of acid-base titrations. So we're not going to talk about redox titrations, we're not going to talk about acid-base titration curves, what happens when you titrate a weak acid with a strong base, etc. We're really just doing the stoichiometry here. And we're going to do some practice problems as we go. Let's talk about the titration process. I've got a solution in a burette. The stopcock is in the closed position. And then I've got another solution in a flask underneath the burette. The solution that's in the burette is referred to as the titrant. And for the purposes of this webcast, let's assume we know the molarity of it. Now the solution that's in the flask is referred to as the analyte. We're titrating the analyte with the titrant. And for the purposes of this discussion, let's assume we know the volume of the analyte, but we don't know its concentration. Now, in an acid-base titration, you'll often add an indicator to the solution, and the indicator is going to change color when I've added enough titrant. In terms of the measurements, I can measure that initial burette reading, and I'm going to do that very precisely according to the markings on the burette. And then I'm going to open up the stopcock and slowly add titrant to the flask, and I'm going to keep doing that until the indicator changes color. And then I'll stop adding titrant and I'll close the stopcock again. That color change is often referred to as the end point. The other measurement that we need to make is the final reading of the burette. And again, we're going to record that very precisely. The reason that's important is because the difference of the initial burette reading and the final burette reading gives us the volume of titrant that we added. So when you're doing a titration, there are really 4 pieces of information you need to do the calculations. You need to know the volume of titrant used, you need to know the molarity of the titrant, you need the molarity of the analyte, and the volume of the analyte. You know 3 out of the 4, and the titration calculation will allow you to calculate that missing piece. So what we're talking about here is an example of volumetric analysis. We're doing volume measurements to figure something out. There are a lot of uses for that, calculating the concentration of an aqueous solution, and we can also use it to find the molar mass of an unknown acid. This is especially relevant when the acid is a solid and we can mass the amount of acid used. We're going to go through and do some problems like that so you can see how that works. Let's talk about our general strategy for solving these problems. You really need to keep in mind that these are stoichiometry problems. So you want to start with a balanced equation. From the balanced equation, we can pull out mole-to-mole ratios. I'm going to tell you, sometimes just the information about what the reactants are is enough to get the mole-to-mole ratios, even if you didn't write out a balanced equation. But you really do want to have that. For acid-base titrations in particular, what you need to remember is at the equivalence point, the moles of base that you added from the burette equal the moles of acid that were present in your flask. Or really what I should say is they're reacting in the mole-to-mole ratio in that stoichiometric proportion that we get from the balanced equation. For a lot of them, they are in a 1-to-1 ratio. And if the acid and base are reacting in a 1-to-1 ratio, at the equivalence point, we can say that the molarity of the acid solution times the volume of the acid solution equals the molarity of the base solution times the volume of the base solution, because that would be moles of acid equals moles of base. And this is really handy. If they don't react in a 1-to-1 ratio, then you're going to need to use the molarity formula and the mole ratio. The molarity formula is really important when you're doing acid-base titrations and those calculations. I've got a webcast on the molarity formula, and if you don't feel comfortable with the molarity formula, you might want to go watch that and then come back to this webcast. So let's go through and work through a sample problem. A student uses 34.88 milliliters of 0.156 molar potassium hydroxide to neutralize a 26.55 milliliter sample of nitrous acid, HNO₂. What is the concentration of the nitrous acid solution? Let's look at what we know. We know we have potassium hydroxide. There's 1 hydroxide in that formula. And we have nitrous acid, which is a monoprotic acid. So even without writing a balanced equation, I know that these two are going to react in a 1-to-1 ratio. And that means I can use my favorite equation, which, by the way, is not on the formula sheet. So we can say MAVA equals MBVB. Well, what we're solving for is the concentration of the nitrous acid solution. So we can rearrange our equation to solve for the molarity of the acid. I'm a big fan of rearranging before I substitute. If we go back and read through our problem, all right, we can substitute and evaluate because we have all the information. It's there. All right, I know the volume of the base that was used. I know the molarity of the base that was used. And I know the volume of the acid that was used. And I can substitute all of this in. I want to point out one of the handy things about MAVA equals MBVB is that it doesn't matter actually what concentration unit it is. It doesn't have to be molarity. it has to be the same on both sides. I don't have to be in liters. I just need to have the same volume unit on both sides. And if you look at my rearrangement, the unit of milliliters is going to cancel out, and it's going to leave me with molarity, which is what I want. I can substitute everything in. I can get out my calculator. I get an answer of 0.205 molar nitrous acid. I knew my molarity to 3 sig figs, so I can only have 3 sig figs in my final answer. All right, let's do another problem. A student uses 31.72 milliliters of a 0.125 molar sodium hydroxide solution to completely neutralize a solution containing 1.08 grams of an unknown monoprotic acid. Calculate the molar mass of the unknown acid. Now this one, we got to think here a little bit. I know the molarity and volume of the NaOH, but I only know the mass of the monoprotic acid and that it's monoprotic. Because it's one hydroxide and sodium hydroxide and a monoprotic acid, I do know that they're going to react in a 1-to-1 ratio. So that's a handy thing to know. But I have to remember that at the equivalence point, right, all of this means the moles of added sodium hydroxide equal the moles of the unknown acid. And I don't know what acid it is. I don't know its formula. I know I had 31.72 milliliters and I have 0.125 molar. So I know that the molarity of the NaOH is moles divided by the volume in liters. So I can rearrange that to solve for moles of sodium hydroxide. So the molarity times the volume. I can substitute those values in, convert my milliliters to liters, and I get 0.003965 moles of sodium hydroxide. Now, if you're being really attentive, you realize I only know my molarity to 3 sig figs, and so I really only know my moles of NaOH to 3 sig figs, but I don't want to round right now because it'll introduce a rounding error. I'll take care of that at the end. Remember, the moles of sodium hydroxide equal the moles of unknown acid that I neutralized. And so I know the moles of acid equal the moles of NaOH. We also know from our experience in chemistry that molar mass is defined as grams over moles. Well, I know the grams. That was given in the problem. And I know the moles because I just calculated it. So I can substitute in the grams and the moles, and I get a molar mass of 272 grams per mole. I'm going to report that to 3 sig figs. One more problem. A student uses 16.80 milliliters of 0.225 molar potassium hydroxide to neutralize a 26.55 milliliter sample of sulfuric acid, H₂SO₄. What is the concentration of the sulfuric acid solution? So again, we have potassium hydroxide. There's one hydroxide in that formula. And I've got sulfuric acid. Sulfuric acid is a diprotic acid. There are 2 hydrogen ions. And so it's not going to react in a 1-to-1 ratio. We can't just do MAVA equals MBVB. You're not going to get the right answer. A good starting place would be to write that balanced equation. And when we write the balanced equation, we see that there are 2 hydroxides that need to react for every sulfuric acid. That 2-to-1 ratio. That's going to be really important. So our strategy here is we can use the volume and the molarity of the base to find the moles of KOH. And once we know the moles of KOH, we can use our mole to mole ratio to find the moles of H₂SO₄. If we now know the moles of H₂SO₄ and we know the volume of the H₂SO₄, we can calculate the molarity. And so that's the first way to solve this problem. There's another way. Just hold on. I'm going to walk you through that too. So I can find the moles of KOH just like we did before, but this time I'm going to work in millimoles. So I'm not going to convert my volume to liters. I'm going to keep it all in milliliters and I'm going to work in millimoles because I just like millimoles. All right. It can be really handy. It saves a little time. But you have to make sure you're paying attention to what you're doing, okay? So I can solve for the millimoles of KOH would be 3.78 millimoles. I could, of course, do this in moles as well. I'm just not. And then I know that there's that 2-to-1 ratio. So if I have 3.78 millimoles of KOH that reacted, I'm going to have half as many moles of sulfuric acid, or 1.89 millimoles of H₂SO₄. I know molarity is moles over liters. Well, the proportion would be the same if I do millimoles over milliliters. Comes out to be the same. And so I can substitute that in. I have 1.89 millimoles. I have 26.55 milliliters. I could, of course, do this all in moles and liters, but I like shortcuts that are legit. And I get 0.0712 molar sulfuric acid. Now, I mentioned that there was a second way to do this problem. It's kind of a shortcut, but not really. It's totally legit. You know you want to hear it, right? It's going to save you time. This is worth sitting through. So a second version of this problem takes into account the fact that we know that the ratio is not 1-to-1. We're going to do this by modifying MAVA equals MBVB. How do we do this? Well, we have to look at the formulas, all right? And we're going to multiply the acid side of MAVA by the number of hydrogen ions in the acid formula, which I've called here number of H+. And on the hydroxide side, the base side, I'm going to multiply that by the number of hydroxides in the formula. And this is going to take care of all my mole ratios for me, and I don't have to write a balanced equation or anything. I know there's one hydroxide in the base formula. There are 2 hydrogen ions in the acid formula. So when I rearrange my equation, I can substitute that in. I need to put a 2 on the acid side and a 1 on the base side. And then I know the molarity of the base. I know the volume of the base, and I know the volume of the acid. I can rearrange this equation to solve for the molarity of the acid, which is, of course, what we want. I can substitute it all in, and I get the same exact answer as I got in the other version of how to solve this problem. But this can be a very handy shortcut. It's not really a shortcut. It uses a principle called normality, which we don't actually teach in AP chemistry, but normality is where you multiply the molarity by the number of ionizable hydroxides or the number of ionizable hydrogen ions. So you're talking about normal solutions instead of molar solutions, and that's really what we're doing here. It's totally legit, and it gets you the right answer. You just need to make sure you show your work. As a final wrap up, make sure you read the question carefully. Make sure you know what you're solving for. List out the variables that you're given. You can only use MAVA equals MBVB if it's a 1-to-1 ratio, but we know that we can modify that equation when it's not a 1-to-1 ratio. But you got to stay on your toes and think through what you're doing. There can be more than one way to solve a titration problem, as we showed. Make sure you show your work and use a valid strategy. That's my advice when you're doing these problems. If you found this helpful, like the video, leave a comment, subscribe to my channel so you get all my latest updates. Have a great day and keep studying chemistry.